do you do it? Look at up there balancing. She's a big bird on a little stick. How does she do it? How does she do it?
Hi everybody! My name is Sarah and I'm excited to share some center of mass demos with you today. I was inspired by my backyard chickens, and as you saw in the first video, they balance so gracefully, but they're big birds. Anyway, before we get into the demos, let's define some terms. So the center of mass is the point of an object where the average weight is located. It's a singular point where the weight acts on the object. There is no turning effect if a force is applied at this point, and we can see in the picture there's a few examples. I'd like to point out that these shapes are all symmetrical, so we can see that the center of the mass is in the middle. In the case of the object second from the left, we can see that the point is not within the shape. And this is a good thing to remember, that our center of mass does not necessarily need to be within the shape. Finally, I'd just like to point out that today we're talking about center of mass, but it's also sometimes called center of gravity. There are some very fine differences between these two, but in general, they can be used interchangeably. The second important definition is equilibrium, and there are two types of equilibrium, stable and unstable. I'll provide a brief explanation for the difference between the two, but today we'll be focusing on stable equilibrium. When a system is in stable equilibrium, its center of mass is directly below and in line with the resting point, or the point of support. The system in stable equilibrium will always return to its equilibrium position. So here's my quick explanation. On the left, Yoshi is in stable equilibrium when he's rolling along Rainbow Road. If he were to roll forward or backwards, eventually he will return to the position he is in, at the bottom of Rainbow Road. On the right-hand side, however, if he moved forward or backward, he would not naturally return to the peak of Rainbow Road. This is unstable equilibrium. So now we know our definitions of equilibrium and center of mass. So let's look at an object and see how this goes. So this ruler is symmetrical, halfway point, it's the same on either side. And the other important thing to remember is that its density is the same across its whole the whole length of the object. So there is some cork and there's some steel on the top, but it's the same all the way across. So that's important to remember because the differences in density can change where the center of mass is located. So, because it's symmetrical, we knew that our center point is going to be our center of mass. But as soon as I move my finger to the side of this ruler, what do you think is going to happen? You're right, it rotates and falls down. So this is what this turning movement is that was in the definition. So now for the demo. What about a shape that is not symmetrical? It's 2D, it has the same density, but it's not symmetrical. What are we going to do? So for this, I cut out a province of British Columbia. So the materials that you need to do this demo, and I'm going to use a demo called the hang test. The materials you need is an obscure shape. Cardboard works better. You need a little bit of weight for it. You'll also need a string with a weight just so that it hangs straight down. And I've got a pencil, but you can also use a pen. I just don't want to make a mistake, so I'm going to use a pencil. So how this hang test works is that our center of mass, we know, lies in line and underneath our point of support. So in this case, my point of support is going to be my pinched fingers. And we can still see that it can rotate, so I'm not holding it, I'm not gonna fake it, that the obscure shape can still rotate. So I'm gonna take my weighted string, I'm gonna add it to my pinch point. See, this can fall, I'm gonna let it settle, and then we see we have a line. So I'm going to draw that line. So we have our line number 1 dotted down. So what about another point? Because this is just a line and we need a point. We know that there's a point that exists for our center of mass. So I'm going to try the middle. And again, we can see that this is rotating and it can settle into a balanced state. And I'm going to add my weighted rope, and again I'm going to draw this. Okay, so we can see the two lines intersect. But to be thorough, let's do one more point. And I'm going to pick this one up here. So we've got two corners in the middle. So again, pinch it, let it fall. I'm going to just secure it here. Let it fall. Secure it. And I'm going to draw this line. And would you look at that? Based on all of the lines that I've drawn from our three different hang tests, we can see that the point in the middle of this shape, the centroid of this 2D shape, is somewhere in between Terrace, Prince George, and Bella Bella in here. So now you know. Here are some other fun demos that explore our understanding of center of mass and equilibrium. First up, try balancing a pencil tip down on your finger. See how long you can hold it up there for. I bet you can't do it for more than a second. Let's see how long I was able to balance the pencil for. Clearly not very long. This time, I'm going to use some wire that I'm going to wrap around the pencil and a butterfly clip, just like one that you can find at home or in your classroom. I'm going to attach those two together. And here I am wrapping the wire around the pencil. So now I'm going to put the pencil on my finger, and the tip of the pencil is our point of support. And look at that. Now that the weight, the center of mass in the butterfly clip is below the support, just like we learned, it is able to balance better. And let's see what happens when I bend the pencil sideways. Is it still going to balance? Let's take a look. Oh, almost. Hey, there we go. Even at an angle, the center of mass is still below the point of support. Here's another demo of equilibrium and center of mass. In this case, similar to the pencil, we have our point of support lying above, directly in line with the center of mass, which lies somewhere in the handles of the two forks. And this system is balanced on either side. We can see it's not touching the wine bottle. There's no tricks here. These two forks are balancing on the edge of the toothpick because their center of mass lies directly below. So now, I'm sure you've all been wondering, just like I was, how do my chickens balance? Because of the position of our center of mass and our legs and feet, we are able to balance. Similar to the chickens, their center of mass is above their hip bones. So because of their large feet and the distance between their legs, they're able to balance. So this isn't exactly a connection between center of mass and the demos that I've shown you today, but it is a good application of how center of mass helps us in our day-to-day lives. Kind of like Riley balancing on the wall. So Riley is going to try and touch his toes. Right now his heels are on the wall. So he's going to try and touch his toes with his heels on the wall. He can't touch his toes normally. Okay, so he couldn't do it with his knees straight, just bending down, because his center of mass would move too far forward and he would fall down. But instead, sneaky guy tries to lower his center of mass so that he can touch his feet, but still can't bend that way. So why don't you try this at home? Thanks for watching my video. I hope you learned something new today about center of mass and equilibrium. Make sure to try some of these demos at home. They're lots of fun and not a lot of materials are required. Thank you. If anyone wants to extend their learning, Physics Classroom has a great center of mass builder where you can build any shape you please, and it will help you find its center of mass point.